Here is a result that should make any machine learning practitioner stop. A linear model trained on a housing dataset, square footage, number of bedrooms, neighborhood score, produces an R-squared of negative 0.18. It performed worse than simply predicting the average home price for every observation. Not weak signal, negative signal. The algorithm did not fail, the features failed it. And that is the argument at the center of this video. Linear models occupy a unique position in applied machine learning, not because they are the most powerful, but because they are the most transparent. Every prediction a linear model makes is a weighted sum of the input features. Price equals some weight on square footage, plus some weight on number of bedrooms, plus a baseline. Those weights are the coefficients, and they are directly readable. A large positive coefficient pushes predictions up. A large negative coefficient pulls them down. A coefficient near zero means the feature is contributing almost nothing. This transparency is not just convenient, it is diagnostic. When coefficients are unstable, extreme, or pointing in the wrong direction, the model is telling you something important about the features you gave it. To build intuition for linear models, consider a simple housing price example. 3 features: square footage, number of bedrooms, and a neighborhood score. 1 target: home price. The model's job is to find the weights that best explain the relationship between those inputs and that output, minimizing the gap between what it predicts and what the prices actually are. This is ordinary least squares, the simplest form of linear regression. No penalty, no regularization. Just find the weights that minimize prediction error on the training data. In theory, with clean features and enough data, this works well. In practice, something more interesting happens. The ordinary least squares result on the housing data is striking. R-squared of negative 0.18, mean squared error of 1.45 billion. The model assigned a coefficient of negative 50,000 to the number of bedrooms, an extreme, unstable weight that reflects noise in the training data, not a real relationship. When features are correlated or the dataset is small, ordinary least squares has no mechanism to prevent this. It will chase the noise and memorize the training data instead of learning the signal. Ridge regression changes one thing. It adds a penalty for large coefficients. The model is no longer free to assign extreme weights to any single feature. The coefficients are shrunk towards zero, and the model is forced to distribute importance more carefully across the features. The result on the same dataset: mean squared error cut by more than half, and an R-squared of 0.55. The algorithm did not change. The regularization changed what the algorithm was allowed to do with the features, and that is what changed the outcome. Lasso takes regularization one step further. Where Ridge shrinks coefficients towards zero, Lasso's L1 penalty can, in the right setting, push some coefficients all the way to exactly zero. That matters because a coefficient of zero means the model has stopped using that feature entirely. In a simplified coefficient example, square footage, bedrooms, and neighborhood score all remain active, but wall color and decorative style are pushed to zero. That is built-in feature selection. The model is telling the practitioner that those features do not earn their keep. But in applied machine learning, the point is not just to admire the theory. The point is to see what happens when the full workflow is run on a real example. So start with the dataset. In this housing example, the model is given square footage, number of bedrooms, and neighborhood score as inputs, and home price as the target. Then train the 3 models on the same data: ordinary least squares, Ridge, and Lasso. Same dataset, same prediction task, different regularization behavior. Now evaluate the results. OLS performs poorly with a negative R-squared. Lasso, in this small 3-feature example, performs much like OLS. Ridge is the clear improvement, cutting error substantially and producing a positive R-squared. and the learned coefficients explain why. OLS assigns unstable weight. Ridge shrinks those weights into a more stable range. Lasso changes them too, but in this particular applied example, it does not eliminate any of the three features completely. That contrast is the real lesson. Lasso can perform automatic feature selection, and when weak or irrelevant features are present, it can push them to zero. But whether that happens depends on the data, the features, and the problem. And that brings the point of this video into focus. Feature quality determines what a model can learn. Regularization can stabilize a model. Lasso can simplify a model. But neither one can create signal that the features do not already contain. The same principle extends directly to classification problems through logistic regression. Instead of predicting a continuous value, the model predicts the probability of a binary outcome. Will a house sell above or below the median price? Will a borrower default? Is this email spam? Logistic regression still builds a weighted sum of the features, but instead of outputting a number, it maps that value into a probability between 0 and 1. Apply a threshold, and the model becomes a classifier. In practice, the workflow looks almost identical to linear regression. We still split the data, fit the model, generate predictions, and evaluate performance. The pipeline stays the same, only the type of prediction changes. Once the model makes predictions, we evaluate it using classification metrics like accuracy, a confusion matrix, and precision and recall. These metrics help us understand not just how often the model is correct, but what kinds of mistakes it makes. Regularization still matters here, and in logistic regression, the control for regularization strength is the C parameter. Smaller c means stronger regularization. Larger c means weaker regularization. In other words, C controls how freely the model is allowed to assign large weights to features. So even though we changed from predicting numbers to predicting probabilities, the model is still learning from features, still assigning weights, and still affected by regularization. The algorithm changes. The feature logic does not. Consider a full case study using the OpenML Diamonds dataset, about 54,000 observations with price and attributes including carat, cut, color, and clarity. The same pre-processing pipeline can support both a regression problem, predicting price, and a classification problem, predicting whether a diamond falls above or below the median price. Ridge and Lasso models can select their regularization strength through cross-validation. And when you plot the Lasso coefficient path, you can see exactly which features get pushed to 0 as regularization increases, a direct picture of which predictors the model considers dispensable. But there is an important point here that goes beyond model performance. The quality grades assigned to diamonds, cut, color, clarity, are market conventions shaped by human judgment. They are contextual signals, not measures of inherent worth. If you deploy a price prediction model built on these features, the model is learning human valuation, not intrinsic value. That means the features you choose and what they represent are an ethical decision as much as a technical one. Chapter 3 of Applied Machine Learning, Concepts, Tools, and Case Studies walks through these examples end to end. The housing price experiment, comparing ordinary least squares, ridge, and lasso. The coefficient interpretation tables, the logistic regression exercises, and the full diamonds case study pipeline. The goal is not just to show the models, but to show the workflow and the reasoning behind each decision. If this is how you prefer to learn, seeing the full process step by step, the link to the book is in the description. Linear models give you one of the clearest views of how features influence predictions, but they come with an important assumption. They assume the relationship between the inputs and the output is linear. Many real-world problems are not linear. Price does not always increase in a straight line. Risk does not always increase in a straight line. Human behavior is rarely linear. In the next video, we look at the models that dominate production systems when that assumption breaks down. Tree-based models, random forests, and gradient boosting. Features determine what a model can learn. Algorithms determine how efficiently it learns what the features allow. If the features do not contain the signal, no algorithm can recover it. Get the features right first. See you in the next video.